This is a fun video because we're going to solve a problem, and I'm not going to tell you how to solve the problem until after we do. So the question is, how do we solve initial value problems? And the answer is, let's figure it out. So solve the initial value problem. dy dt equals 2, 3, 0, negative 4 times y. So this is our coefficient matrix A. We could rewrite this whole thing, right? We could say dx dt is equal to 2x plus 3y, and dy dt equals just negative 4y, right? These are equivalent ways of writing the same system of equations. Oh, I should probably give you an initial condition, huh? Oh, that's odd. I didn't write down the initial condition. It shouldn't matter. Let's say the initial condition is 1, 1. I'm going to regret this. I'm going to regret this. I did not write down the initial condition. I'm sure it'll be fine. All right. Making up a math problem never hurt anyone. It never made numbers not nice. So how do we solve this initial value problem? Well, remember when we had first order differential equations, we solved the initial value problem by just finding the general solution and then plugging things in to find what C is. Well, I haven't told you how to find the general solution to these problems yet, but we do know how to find solutions, right? This is a decoupled system. We talked about how to find solutions in the last video. So let's find a solution and see what happens. So in 2.4, not the last video, but section 2.4, we talked about it because this is a partially decoupled system. dy dt depends only on y. In fact, we know the answer to this immediately. All right, that says y is a function of t. It's just some constant times e to the negative 4t. Well, that was easy. And then what does this differential equation become? This differential equation now becomes dx dt is 2 times x plus 3 times y, which is some constant times e to the negative 4t. And we can solve this differential equation, right? This is a linear differential equation with constant coefficients. It's non-homogeneous. We could use integrating factors, or we could use the guess and test method because we know our answer is going to be of the form e to the negative 4t. So we know our solution x, right? X is going to be of the form alpha e to the negative 4t. That's going to be our guess. So we plug in. What does the left-hand side become? That's going to be negative 4 alpha e to the negative 4t. We need that to equal 2 times x, which is alpha e to the negative 4t, plus 3 times this constant times e to the negative 4t. And what you'll notice is that everything has e to the negative 4t, so we don't care about that. This needs to be true for all t, so we just need to make the coefficients equal to each other. So negative 4 alpha is equal to 2 alpha plus 3k. And when we do that, we get negative 6 alpha is equal to 3k. So we get alpha is k over negative 2. I don't have an answer to check because I'm making up this problem. Okay. So what do we have? We have an answer. All right, we know that's y, and we know x, right, is negative k. I guess we don't need k1 or k2, right? It's just negative k over 2 times e to the negative 4t. We have an answer. So I'm pausing because I'm kind of solving this problem with you. I really am kind of leaning hard into let's discover this together. So what do we know? We have an x of t, we have a y of t. We need it to satisfy this initial condition. And my guess is, if I remember correctly, is that we're going to get something very interesting when we do this. Let's find out what k has to be. You ready? You're not going to like this, I think. Or one of us is not going to like this, depending on what happens. Right? So we need x of 0 to equal 0. Right? X of 0 needs to equal 1. Right? That's our initial condition. X equals 1, y equals 1. So if x of 0 has to equal 1, then what we get is that 1 equals negative k1 over 2. This becomes 1. And so we get k1 is negative 2. Okay. So we have our solution, right? No. Because k1 equals 2, right? We do have a solution, just not to the initial value problem. We found that y of t, right, is, let's see, k1 is negative 2. So x just becomes e to the negative 4t. And y becomes negative 2 e to the negative 4t. So this is a solution. But the problem is, our solution has a bit of an issue. That's our initial condition. That's not the right initial condition. I didn't mess up though. I gave us an initial condition. We can find a solution that satisfies this initial condition. So what do? We remember our linearity principle. Our linearity principle says, okay, I can multiply this solution with whatever number I want and still get a solution. But again, that part's not going to be helpful, right? Because multiplying this solution by 5 just makes this 5, negative 10. Well, that's still not good. We could divide this by negative 2 to get 1, and then this part's negative a half. Again, that's not right. But remember, the linearity principle says that if we have two solutions, any linear combination will also be a solution. So this is actually our y1. This is one of our solutions. We need another solution. If we can find another solution, maybe we can add or subtract them. Remember all the way back to when I talked about linear algebra, and I said if we had two linearly independent vectors, that could be used to make any other vector with a linear combination. So if we can find another solution that has some kind of linear independence, we can definitely get our initial condition satisfied. So we get to solve this differential equation again. We found one solution, yes, but what about second solution? There's some Lord of the Rings meme that I could make there. How can we find another solution? Well, I don't know. We kind of only talked about one way of solving decoupled systems. And that's where sections 3.2 and 3.4 are going to be helpful, right? How do we find more solutions? How do we find the general solution? So you don't need to know how to do this next step. I want you to be able to recognize that we need another solution, but I don't need you to know where this is coming from or to be able to do it yourself. But let's just see, well, what happens if y is 0, right? If y equals 0, something very nice happens, right? dx dt, let's just copy down our system, right? dx dt is 2x plus 3y, and dy dt is just equal to negative 4y. Well, if y equals 0, well, then this equation's satisfied. And then what does dx dt equal? Just 2x. So if y equals 0, that's another way of getting a solution. And again, you don't need to know where this comes from necessarily. Then x of 2, we could solve this differential equation. It's going to be some constant times e to the 2t. So we have a solution. We found another solution, right? y2 of t was when x is any constant times e to the 2t. Let's not call it k1. And y is 0. Because specifically what we notice, what's the initial value of y2? It's k comma 0. We look at these two vectors. We say, are these vectors linearly independent? Yeah, they're not multiples of each other. I can create any vector I want out of a linear combination of these two vectors, right? If I were to graph some vectors, one of these vectors, the x component, can be anything we want, right? That's y2 of 0. And the other one is 1, negative 2. We need to create the vector 1, 1. So we can get this yellow vector 1, 1 with a linear combination of these other two vectors, because green and blue right here are linearly independent. Okay. So here's what we're going to do. We actually don't need this k here, because we're already going to be doing a linear combination. We're going to find the linear combination of these two solutions that gets us our satisfied initial condition. Okay? So our solution is just going to be, by the linearity principle, we know that y1 times some constant, any constant, right, is a solution. So what is this? That's going to be any constant times this first one. So k1 e to the negative 4t plus k2 e to the 2t and then k1 negative 2k1 e to the negative 4t plus k2 times 0 is a solution. Let's call this y of t. It will turn out for us that this is actually a general solution. But we haven't introduced that yet, how to find general solutions. Okay, and again, we want y of 0 to equal 1, 1. So we have a system of equations, right? What is y of 0? That's going to be k1 plus k2 and negative 2 k1. So, right, if we solve this, right, if we set this equal to 1, 1, what are we going to get? We're going to get k1 is equal to negative 1/2. And so k2 is going to equal 3/2, I think. Wait, because negative 1/2 plus 3/2, yep, good. So we'll find out that our solution to this initial value problem is negative 1/2 e to the negative 4t plus k2, which is 3/2 e to the 2t. And then the y component is negative 2 times k1, which is just positive 1, I believe, e to the 4t. Sorry, e to the negative 4t. And there we have it. Okay? This satisfies our initial condition. We can check by plugging in 0. If we plug in 0, we get negative 1/2 plus 3/2. That's 1. And we get 1 for the bottom as well. So we have now found our solution to this initial value problem. Just need to find two solutions. As long as they're linearly independent, we can then find any linear combination and still be a solution. And we can actually find any any vector, any initial condition we can find. And that's why I knew that I could make up an initial condition, because as long as our solutions that we found were linearly independent, we can solve any initial value problem actually. And furthermore, since this system is nice enough, this solution is actually unique. Okay, if you give me an initial condition, this has to be the solution. There is no other solution here. We kind of skipped that section. That was 2.6, talked about uniqueness of linear systems. And again, it's going to be pretty similar requirements to in chapter 1. Basically, as long as everything's nice enough, we're going to have uniqueness. If you look at the phase portrait, solutions are not really going to cross, as long as it's autonomous. If it's non-autonomous, it could look like it's crossing because we sort of have a third dimension. I'm really getting into some other stuff, but again, There are plenty of videos out there for what it looks like to have uniqueness for systems of differential equations, but we don't really have time to cover that. So we'll just kind of hand wave it and say, if you're nice enough, everything will be fine. That's pretty much it for this video. That's how we find and solve initial value problems. Again, the last thing I want to say is, what did we do? Right? First, we found two solutions. And again, how do you find those two solutions? We talk more about that in the next couple sections. You don't really have to know how to do this step very much. All right, and then again, remember, we look at a linear combination of those two solutions to satisfy the initial condition. And that's basically it. It's the linearity principle. Hope you enjoyed the video. We'll close this section on another video. Again, I do know this section is quite long. Another video on how do we find general solutions, and we'll tie that into the undamped harmonic oscillator. Because again, what more would you want to talk about in a differential equations class other than harmonic oscillators? Bye-bye.